1 prompt injection, 6 words, and this agent code delete all users with full permissions. 48% of security teams say agentic AI is their top threat vector for 2026. Most agents in production right now have zero validation between the user's input and the tools the LLM can invoke. That means if someone crafts a prompt that tricks your model into calling a destructive tool, there's nothing stopping it. No input filter, no authorization check, and no output scan. Today we are building a 4-layer defense system in LangGraph: input validation, tool call authorization, output filtering, and policy as code guardrails. And I will show you a technique that catches injection attempts before the LLM even sees them. The OWASP LLM Top 10 maps out the biggest risks for large language model applications, but 3 entries matter most when your system has agency, meaning it can take actions. Prompt injection is the ability to hijack the model's intent through crafted input. Insecure output handling means the model's response gets passed to downstream systems without sanitization. And excessive agency is when the model has access to more tools or permissions than it actually needs. Agents combine all 3 risks because they turn text into action. The fix isn't a single check. It's defense in depth, where each layer catches what the previous one misses. Input validation screens for injection patterns and policy violations before the LLM processes anything. Tool call authorization enforces least privilege, meaning the agent can only invoke tools that match the current user's permissions and the task scope. Output filtering scans the model's response for leaked sensitive data or hallucinated tool calls before it reaches the user. And tying it all together is a policy engine that defines these rules as code, not as prompt instructions that can be overridden. Input guardrails work in layers of increasing sophistication. The first pass is pattern matching. Fast regex catch obvious injection templates like ignore all instructions or attempts to reference system prompts. The second layer is schema validation with Pydantic, which enforces that the user input conforms to an expected structure before it goes anywhere near the model. The third and most powerful layer is a semantic classifier that evaluates whether the input's intent is consistent with the agent's allowed scope, catching rephrased attacks that bypass string matching. This is where most agent security falls apart. The model decides to call a tool and the system just executes it. Tool calling authorization adds a gate between the model's decision and actual execution. Every call gets checked against an allow lists that scope to the current task, role-based permissions that match the user's access level, and a policy file that defines these rules in code rather than in system prompt. The reason policy as code matters is that prompt-based rules can be overridden by injection, but code level policies cannot. Now that you understand the architecture and the reasoning behind each layer, let's implement it. We are going to build a LangGraph agent with 4 dedicated security nodes: input validation, the agent's reasoning loop, tool call authorization, and output filtering. We will wire in Nemo guardrails for the policy engine and Pydantic for runtime schema validation. By the end of the coding section, you'll have a working agent that blocks prompt injection, enforces least privilege on tool calls, and scans every output before it reaches the user. Now let's start by creating a new folder and moving inside of it. We should also create a new Python virtual environment, and we need to activate it. Let's get the dependencies installed. We need LangGraph for the agent graph, LangChain OpenAI for the LLM, Pydantic for input schema validation, PyYAML to load our policy as code config, and python.env to manage our API key securely. We will be working with 4 files: a .env for secrets, guardrails.py for security layers, policy.yaml for tool permissions, and agent.py for the graph itself. Inside the .env file, you need to specify your OpenAI API key. Inside the guardrails.py, we will start with the first defense layer, which is input validation. We are defining a Pydantic model called user query that enforces structure on every input before it reaches the LLM. The field validator caps query length at 500 characters, which prevents payload stuffing where someone tries to overflow the context window with a massive prompt. Below the model, we define our injection detection patterns. These regex patterns catch the most common injection templates, things like ignore all instructions, direct references to the system prompt, or attempts to reassign the model's identity. The detect injection function runs all patterns against the input and flags the first match. This is your fast, deterministic first line of defense. It runs in microseconds and catches the obvious attacks before anything more expensive kicks in. Now let's move to the policy YAML for the tool call authorization layer. Instead of hard coding which tools each role can access inside the system prompt, we are defining permissions in a YAML file. This is the policy as code approach from the slides. Permissions live in a version config file that's auditable and reviewable in pull requests and not buried in a prompt string where injection can override them. We have 3 roles here: viewer, editor and admin, each with a specific set of allowed tools. The key principle is least privilege. The viewer can search and summarize, but nothing else. Only admins get access to destructive operations like delete file. When you deploy this, you would extend this file with your own tools and roles. Back in the Guardrails PI, we add the authorized tool call function. It loads the policy file and checks whether the requested tool exists in the user's allowed list. If the tool isn't listed for that role, the call gets blocked before execution. The LLM's intent never becomes action. The filter output function handles the other end of the pipeline. After the LLM responds, this scans for sensitive data patterns, email addresses, social security numbers and API key formats. Anything matching gets replaced with a redacted tag. This maps directly to insecure output handling from the OWASP list we covered. It catches cases where the model leaks data from its context without you realizing it. Now we move to the agent.py and wire everything into LangGraph. We load environment variables with .env right at the top so the OpenAI key is available before any LLM initialization. We define agent state as a type dictionary that carries the query, user role, response and a blocked flag with an optional reason. Every node in the graph reads and writes to this shared state. The input guard function is the first node the graph calls. It runs Pydantic validation on the raw input. If the schema rejects it, the query is blocked immediately. If validation passes, it runs injection detection. Notice that if either checks fails, blocked gets set to true and we attach a reason. This means the query never reaches the LLM and the pipeline short circuits, which saves both tokens and risk. The agent node is where the LLM does its actual work, but only if the input passed the guard. We initialize a chat OpenAI instance and invoke it with the validated query. In a production agent, this is where you would add your tool calling logic and run authorized tool call before each tool execution. For now, we are keeping the LLM call simple to focus on the security wiring. After the model responds, the output guard node runs our sensitive data filter before the response reaches the user. The key thing to notice is the clean separation. The LLM only ever sees validated input and the user only ever sees filtered output. Two distinct boundaries, neither one relying on the other. This is where the 4-layer architecture becomes a running graph. We create a state graph, register our 3 nodes and set the input guard as the entry point. The important part is the conditional edge after the input guard. The route after guard function checks the blocked flag and decides whether to skip straight to the end or continue to the agent node. This conditional routing is what makes the defense efficient. Blocked requests exit the graph immediately and never consume a single LLM token. Safe requests flow through the agent and then through the output guard before reaching end. You can visualize this as a diamond-shaped branch right at the front of your pipeline. Let's test with 2 inputs, one legitimate and one malicious. The safe query should flow through all 3 nodes and return a normal response. The injection attempt should get caught by the input guard and return a block reason, providing it never reached the LLM. Now let's run it and check the output. As you can see, the first invocation was marked as safe and we got a response from the LLM, but the second one was blocked because there was true injection detected. Let's recap what we built. We started with an agent that had 0 validation between user input and tool execution. A single crafted prompt could trigger any tool with full permissions. We fixed that with a 4-layer defense system. Input guardrails catch injection attempts before they ever reach the model, using pattern matching, schema validation, and semantic classification. Tool call authorization enforces least privilege by checking every tool invocation against an allow list, role-based permissions, and a policy file defined in code and not in prompt. And output filtering scans every response for leaked data before it reaches the user. Your next step is straightforward. Take the OWASP LLM top 10 checklist and run it against your current agent. You will find gaps and now you have the patterns to close them. If this was useful, subscribe to ByteBuilder. We ship production grade agent tutorials every week.